We've seen that relativity requires us to rethink our ideas of time. Now we need to look at space and distance. We have thrown out our idea of absolute time, that is, time that everyone can agree on. Now there is no time which time for me is the same as time for someone traveling half the speed of light. We've worked out that time itself is relative. But now it's time for us to throw out our idea of absolute space or absolute length, where I might measure something and I measure it as a meter, and so would someone else traveling half the speed of light. They would also measure it at half as meter, and everyone can agree on length or distance in space. So we're going to look at that assumption and see if it's true, and I've already said to you that we're going to throw it out, so it's obviously not true. And we're going to analyze a situation here, very similar to the ones we've looked at before, where we have a reference frame, and this is reference frame S, which is according to just someone's reference frame, and we have a situation here. First, we have a sun, probably could draw that better. That's a sun. And over here, and this is our sun, I should say, not that it's that important, but just so it feels more personal. And over here is Jupiter. And here we have a spaceship. Which is traveling at a constant velocity in this direction. And we're going to look at, as it passes the sun, where sun is at this position, where X sun, and Jupiter is at this position over here, with X Jupiter. And we're going to look at this length to which it travels, because it's going to travel from the sun all the way to Jupiter, and that is going to constitute some length, some amount of meters. And being from the sun to Jupiter, it's going to be a lot of meters. So according to this reference frame, S, they are stationary, and the rocket is traveling at some velocity v to the right, and it's going to travel this whole distance from the sun to Jupiter. Now, if we look at that same situation from another person's reference frame, in this case from the rocket's reference frame, they can see the sun, because we're starting it at, say, t equals 0, it's at the sun. Not that it matters too much, but the sun is here. Might draw it a bit different, a bit better. I wouldn't call it better, but a bit different. And that's at here, so X prime sun, and over here we have X prime in the position of Jupiter. We'll draw Jupiter in. And this was the sun. And again, we have a length, call that L prime, because it's not necessarily the same. We're not having that assumption that the length according to the rocket is the same length according to a stationary observer watching the rocket. So we're calling this L prime, or we'll call this L. So according to the rocket's reference frame, they are stationary, and the sun is traveling this way at negative v, and the Jupiter is also traveling at negative v, while the rocket is stationary. Since it's traveling in an inertial reference frame, it's not applying any thrusters, so it's not accelerating or changing its velocity in any way. And it would see S's reference frame traveling also negative v to the left, but I won't bother drawing that in. So this is according to a stationary reference frame. And this is according to the rocket's reference frame. Now, notice that I'm not making the assumption that L equals L prime. that is something that is an assumption in Newtonian physics or classical physics, but is not going to make the assumption here. So we know from this diagram here that L is equal to, well, it will be the x position of Jupiter, let us say J, minus the x position of the Sun. And we know that L prime, according to this figure, is the x prime position of Jupiter minus the x prime position of the Sun. And since we know from simple motion calculations that velocity is distance by time divided by time, so we know that the distance travelled in this case would be L divided by time, while the distance in this case, or the velocity it's travelling in this case, would be L prime divided by delta t prime. So what I'm saying is the velocities for these two reference frames are the same, because we can see the rocket traveling at a velocity and the velocity can see everything else traveling at the opposite velocity. So we know that the velocities are the same for both reference frames. And since the velocity in this case is distance divided by time, well, the distance traveled by the rocket is L, and the time it would travel is, we say, delta t, we're not sure yet. And this reference frame, the velocity traveled is going to be equal to the L prime, that distance, divided by the delta t prime, the time it takes in this reference frame. And we know from a previous video that delta t does not equal delta t prime. So if this was to agree, you can already see now, if this v equals L over delta t, was to equal L prime over delta t, where delta t does not equal delta t prime, for them to agree, this one can't equal L, where L can't equal L prime. If you don't get what I mean, let's say if we make them equal to each other down here, for L over delta t, which is the velocity in one reference frame, which is equal to the velocity in the other reference frame, and we know these two don't equal each other. So for this to be true, this whole equation, these two can't equal each other. Hopefully you see that, but if you don't, we'll go into it a bit more so you can see for yourself. So since we know that v, or the velocity in one reference frame, is equal to the v in the other reference frame, or we call it v prime, it doesn't really matter, they're both the same. Because the speed or velocity relative between the two is exactly the same. So you might see the velocity traveling at the rocket traveling at some velocity. A stationary observer would see the rocket traveling this direction at that velocity, while according to the rocket's point of view, everything else is traveling at the opposite velocity. So the relative speed is the same between the two, and you would have seen that in a previous video, but it does hold true all the time in this case, where v equals v prime. So we know that L over delta t is going to equal L prime over delta t. And since delta t can't equal delta t prime, or doesn't equal delta t prime for rockets or whatever traveling at a certain velocity, that we know that L is not going to be equal delta L. And we have to find an L value or a delta L value or relationship that is going to satisfy this equation.